Okay, assalamu alaikum and good morning, guys. Welcome back to grade 11 physics by Inspired Teens, where in today's lesson we'll be continuing with a topic called atomic combinations, and we will be discussing intermolecular forces. Hopefully we will be finishing up this section. Okay, so how we're going to structure this is I want to start off with intermolecular forces, and then I want to go through a structured approach to drawing Lewis diagrams. Okay, but we'll do that towards the end, and if we go over time, then we go over time. But that's why I want to just get intermolecular forces done, and then we can move on to the other thing. Okay, so let's have a look. Let's have a look at this, and let's look at the definition of intermolecular forces. Intermolecular forces, or IMF, are forces, intermolecular forces are weak forces of attraction between molecules or between atoms of noble gases. IMF was intermolecular bonds or intermolecular forces versus intramolecular bonds. Intermolecular forces are not the same as intramolecular bonds, one would expect, because they are two different things. Intramolecular bonds exist between atoms in a molecule. Intermolecular bonds exist between molecules or between atoms of noble gases. So let's discuss the difference between intramolecular bonds and intermolecular bonds. So intramolecular bonds, let's just say we have an oxygen bonded to a hydrogen. Now, when we have this oxygen bonded to a hydrogen, okay, this is just a regular H2O molecule, right? This is a regular H2O molecule. And in this case, I have an oxygen bonded to a hydrogen and an oxygen bonded to a hydrogen again. Now, this type of force, before we get, this type of force, this is known as an intramolecular bond. This is known as an intramolecular bond. So what is an intermolecular force? Now, if you consider a glass, okay, of water, a bottle of water, okay, in a bottle of water, there's not just one single H2O molecule that makes an entire glass of water. There's billions of H2O molecules inside a glass of water, for example. So even in a droplet, okay? So what happens is we have billions and billions of these molecules. So this is just a single H2O molecule, really tiny. So between oxygen and hydrogen, we have a bond formed, right? We learned about those bonds. We even learned how to draw the shape of those compounds, and we even learned what type of shape it is according to the VSEPR theory, the angle of the bond, right? We learned a lot about these bonds. These are known as the intramolecular bonds. Now, when we have other atoms, okay, so let's copy paste this guy. Okay, so now let's just draw a few, right? A few water, a few H2O molecules, okay? And when we have these H2O molecules, okay, what forms between them is a bond, is a force. Okay, let's just make them equally spaced. Okay, so between one H2O molecule and another H2O molecule and another H2O molecule, excuse me. Okay, we can see that these bonds are being formed. Okay, these forces. Okay, so the first type of bond that we learned is an intramolecular bond. That's between the molecules. That's between atoms in one molecule. Okay, but then when numerous molecules combined, the force that forms between them, which are these red things, these are our intermolecular forces. Okay, so I hope we understand the difference. All the black lines, those are the intramolecular bonds. Okay, those are the bonds formed between the atoms of a molecule or the atoms of a compound. Okay, and then when we have numerous molecules bonded together, again, we have water. All right, water does not have one single H2O molecule inside, like perhaps a glass of water. Okay, between these molecules forms a force called an intermolecular force. So there's the difference between an intramolecular bond and an intermolecular force. Let's read the definition. Perhaps it would make more sense now. IMF first, intermolecular bond. Intermolecular forces are not the same as intramolecular bonds. Intramolecular bonds exist between atoms in a molecule, and intermolecular forces exist between molecules or between atoms of noble gases. Okay, so that's also another possibility. When we have noble gases between two noble gases, what would form? An intermolecular force. Okay, so here's another diagram, not better than mine, of course. Inside a single molecule, we have the intramolecular bond, and between the molecules, we have an intermolecular bond. Okay, just an interesting fact for you, which I'm pretty sure is true. Okay, you can Google it. There's some fun homework for you. There are more molecules of water, more H2O molecules in a teaspoon of water than there are drops of ocean in the water, in the ocean. Okay, let me rephrase. Let me say that again. There are more H2O molecules in a single teaspoon or tablespoon of water than there are drops of water in the ocean. Yeah. Okay. If your brain is fried for the rest of the lesson now, I totally understand, and it's totally fine. Okay, let's look at the different types of intermolecular forces. Yeah, that's crazy, but it's true. Okay, let's look at the different types of intermolecular forces. Okay, and one of the main important things is this little line on top here. Very small, so I highlight it so that you don't miss it. Which are the strongest intermolecular forces? So before we even discuss them, let's discuss their strength. So the strongest of all intermolecular forces is something called hydrogen bonding. Then we have something called ion dipole. Then we have something called dipole-dipole, ion-induced dipole, dipole-induced dipole, and London dispersion forces. Okay, sounds like gibberish. Let's make sense of it. Let's look at hydrogen bonding. What is hydrogen bonding and how does it form? Hydrogen bonding is a type of dipole-dipole attraction, but much stronger between small, highly electronegative atoms. Okay, so we discussed what's a dipole at some point here. Okay, but it's fine. You can just write it on top. And we can say that a dipole is basically a polar molecule. Okay, and that's where the name comes from, because remember we said the polar molecule, right, has an uneven spread of electrons. So one side is positive, one side is negative, which creates two poles, a negative and a positive pole. So that's why we call this a dipole. Di meaning two, pole meaning the polarity. Okay, we're creating a positive and a negative side. Okay, so a dipole, whenever they refer to a dipole molecule, we refer to a polar molecule. Okay, so that's important. So therefore, it's a type of dipole-dipole force. So all it means is it's a type of polar-polar force. Okay, so essentially what happens, okay, we'll discuss dipole-dipole in a bit. For now, let's just discuss hydrogen bonding. Okay, hydrogen bonding is essentially when we have the elements FON okay, or FNO. I like to remember it as FON, so it's just FON, or NOF, or NFO. Okay, FON is just easier to remember for humans. Okay, fluorine, nitrogen, oxygen. Whenever you have a compound that has a fluorine or a nitrogen or an oxygen bonded to hydrogen, that is when you have hydrogen bonding. An example is H2O. Another example is fluorine and oxygen bonding, I think is FO. Okay, or NO2. No, I lie. NH3, nitrogen bonding to hydrogen. Okay, so whenever we have fluorine bonded to hydrogen, or nitrogen bonded to hydrogen, or oxygen bonded to hydrogen, let's make it fun. Whenever you have any one of these bonded to hydrogen, we create an intermolecular force of hydrogen bonding. Remember, if you look at the list, hydrogen bonding is actually the strongest of all intermolecular forces. So there's a very strong intermolecular force. Okay, these are not in order here. Are they in order? No, they're not in order here, but they just structure it differently. But the correct order is on top. Okay, please keep that in mind. Intermolecular forces involving ions. Now, what are ions? Ions are simply positively or negatively charged elements or compounds. Okay, those are our ions. We call them positive or negative ions. Okay, they're positively or negatively charged. An example is when we take the ion of hydrogen, it's H+. Okay, and all of those examples basically. Now we talk about ion dipole. So remember, we learned what a dipole is. We learned that a dipole is a polar compound. Okay, so an ion dipole is a type of intermolecular force that forms between an ion and a polar molecule. We don't call it ion polar. It's an ion dipole. But because it sounded like gibberish, let's just, like, we're trying to make sense of it, right? It's self-explanatory. An ion and a dipole. As long as you know that a dipole is a polar molecule, which we learned, by the way, what the polar molecule is. Right? Remember, polar molecule is unequal share of electrons. It's non-symmetrical. Okay, so we might have two compounds that don't have the same electronegativity. They form a polar bond, form a polar compound. But remember, at times, according to Vesper theory, we learned that even if there are polar bonds, right, the symmetry of the shape could result in an overall non-polar molecule. Okay, so we learned what polar and non-polar is, right? So polar molecule, right? I'm sure you can think of a compound that's polar, right? So it's forming between an ion, like example, Na plus again, right? Any ion that's suitable to react with this polar molecule. Okay, this is an intermolecular force that occurs between an ion and a polar molecule. Okay, they wrote it, so I'll just get rid of this and opt to highlight this. Okay, which is a dipole. Example, NaCl in water. Okay, so when they say NaCl in water, they're talking about the H plus, reacting with the H plus ions in water, and NaCl, I think it's like this. Which one becomes partially negative? Yeah, should be Cl. Okay, the NaCl, and then the Cl is obviously attracted to the positive ion of the H plus ions in water. Okay, so this is an example. This is our dipole / polar molecule. Okay, and this is our ion. Okay, you can also tell that it's dipole or polar according to its, according to its what? According to its electronegativity difference. Okay, so that's one done out of the park, right? Not so bad. Let's look at the next one. ion-induced dipole. Okay, so whenever you look at induced dipole, you should consider that it is reacting with a it is forming a force or bonding with a non-polar molecule. So here's it here. It says that ion induces a dipole in an atom or in a non-polar molecule. So this is between an ion and a non-polar molecule. Okay. For example, the Cl ion and this non-polar molecule C6H14. Okay. This is our ion. Okay. And this is our non-polar slash ion induced dipole. So our non-polar molecule, in this case, we refer to it as a induced dipole. It's not too important to understand why we call it an induced dipole. But basically, if you remember the word induced from somewhere in physics, right? Induced current, the last section that we did, I think, right? Induced current, induced EMF, induced magnetic field. It's sort of a word that means like created or formed. Okay, so it's an induced dipole. It's a formed dipole. So basically what happens is this non-polar molecule, the negative ions attracted to the positive, so if it's a positive charge, the negative ions of the non-polar molecule. So remember, non-polar molecule is like H2, right? And we said that there's even distribution of electrons, therefore it results in being non-polar. However, when it bonds with an ion, the negatively charged will attract to the positive. All the electrons will move to one side to attract to the positive, creating a partially negative, partially positive. But that's not like too important. The thing that you need to remember is that an ion-induced dipole is basically an intermolecular force formed between an ion and an induced dipole, or a non-polar molecule. Okay, let's have a look at the next one. The next one is a dipole-dipole, and since we know what dipole is, you can guess that intermolecular forces that occur between polar molecules. That's it. Intermolecular forces that occur between polar molecules, same or not the same molecules. Okay, that's also important to understand. It's same or not the same. So example is H2S. So you could have H2S in an intermolecular force with another H2S, or you could have H2S, so they're both polar. H2S is polar, that's polar, so that would be a dipole-dipole. Or you can have intermolecular force with another polar molecule. For example, CH3Cl is another polar molecule, so H2S and CH3Cl also forms a dipole-dipole force because both molecules are polar. Okay, so intermolecular force that occurs between polar molecules, and then they give the example, yeah? And there's it drawn in, right? So this is our dipole, and they both are polar. Okay, then we move over to dipole-induced dipole. So here you can guess what that means. It's a polar molecule bonded with a non-polar molecule. So we have a polar molecule induces a dipole in a non-polar molecule. So it's between a polar molecule and non-polar molecule. Example, O2 in water. Okay, we have our oxygen, which is our induced dipole. Slash non-polar molecule. And we have water, which is our dipole. Slash polar molecule. So here we have a dipole-induced dipole. So the definition for what each force is self-explanatory. It's explained in the name. So hydrogen bonding, FON bonding with hydrogen forms a hydrogen bond, intermolecular force. Ion dipole, it's between an ion and a dipole, which is a polar molecule. Ion-induced dipole, between an ion and an induced dipole. Induced dipole is a non-polar molecule. Dipole, okay? Dipole is between a polar and a polar. Okay, the molecules can be two same polar molecules, two different polar molecules, it doesn't matter. They would still form dipole. And then induced dipole, that's between a polar and a non-polar. Okay. Then we have London dispersion forces, which is also known as the thing we haven't mentioned yet, which is an ion-induced dipole. Ion-induced dipole. No. Sorry, I'm high of something. Induced dipole. It's also known, London dispersion forces is also known as induced dipole, type of intermolecular force. And yes, you can guess what is it between intermolecular force between non-polar molecules. Okay, so two non-polar molecules that form temporary dipoles. Remember I said they form temporary dipoles because they're bonding, the negative of one will attract the positive of the other and vice versa. Okay, so induced dipole. Here we have, shucks, let's just copy paste because we can. An induced dipole non-polar molecule. And next to it, we have an induced dipole non-polar molecule. And together they form a London dispersion force or an induced dipole force. And that's actually the weakest one. Remember, here's the order once more. Hydrogen bonding, ion dipole, dipole, ion-induced dipole, dipole-induced dipole, and London dispersion forces. The strongest being hydrogen bonding, and the weakest being London dispersion forces. Isn't London forces also known as momentary dipoles? Yes, probably that would make sense, because yeah, here's another synonym for the word that you use, temporary dipoles. Okay, so they could also be called momentary dipoles, but the main word that they do use for them, and they should use for them, is London dispersion forces or London forces. Okay, you see the idea of temporary. Okay, remember, it's between two non-polar molecules. When we talk about non-polar, we don't talk about a dipole, right? A non-polar molecule is not a dipole because in a non-polar molecule, there's no dipoles, there's no two poles, there's no polarity being created, a positive and a negative end, right? Because it's non-polar, there's even distribution of electrons. Okay, so non-polar doesn't relate to dipole. However, when the non-polar molecules bond to one another, we have an induced dipole, a momentary dipole, a temporary dipole that forms, okay, because of those bonds, where the positive of one gets attracted to the negative of the other. That's why you see this when you deal with your induced dipole forces. You see these little symbols. Remember, I told you these symbols mean partially or temporarily, I don't know. I think temporarily, whatever, English. Okay, so partially positive, partially negative. So yes, momentary dipoles, that makes sense. Okay, it's just because for the time being they have these so-called dipoles. Okay, but it's not actually a dipole compound. Okay, but yeah, induced dipole between two nonpolars. So yes, those are the 6 different types of intermolecular forces. Not too difficult. Let's highlight this in yellow. Okay, hopefully now it makes sense now that you understand what a dipole is, what an ion is, hydrogen bonding, what an induced dipole is, right? Because then the names are self-explanatory. Okay, so that's the main thing. Knowing the type, right, and knowing the strength is very important because they'll ask you to compare it. Okay, and let's just discuss a few other things. I wonder if we'll find that interesting fact here or just somewhere else. Okay, the amazing water molecule, asymmetrical polar molecule, intramolecular covalent bonds, bent or angular molecular shape, contains hydrogen bonding between molecules. These strong intermolecular forces need a large amount of energy to overcome. So that's the pattern that you'll notice here, right? Intermolecular forces, okay, the stronger it is, right, the more energy it will require. We don't break intermolecular forces, we overcome intermolecular forces. Okay, so the higher the IMF, meaning the stronger the IMF, sorry, the stronger the intermolecular force, the more energy it requires to overcome these intermolecular forces. And you'll see we'll discuss a bunch of properties on the next page, right? But let's continue. Water vapor acts as a greenhouse gas by absorbing the sun's radiation. The ocean acts as a heat reservoir and regulates the temperature of the earth. Let's look at some properties of water. Specific heat capacity, the amount of energy needed to raise the temperature of 1 kg of water by 1 degree Celsius. Water has a high specific heat capacity. So that's the definition of specific heat capacity. A high heat capacity requires more energy for the temperature to change. This helps with heat regulation on the earth. Okay, so it's not easy to change the temperature of water, and it helps with heat regulation of the earth. Of course, if it was easy to just change the temperature of water, that would be a big issue, right? Melting points and boiling points. Strong hydrogen bonding intermolecular forces require large amounts of energy to overcome intermolecular forces. So melting point and boiling point, let's see if it's discussed on the next page. No. But melting point and boiling point, the stronger the intermolecular force, okay, the higher the melting point and boiling point. Okay, because more energy is required to overcome these intermolecular forces. Okay, so strong hydrogen bonding requires intermolecular forces. Strong hydrogen bonding intermolecular forces require large amounts of energy to overcome those intermolecular forces. This water has a melting point of 0 degrees Celsius, and boiling point of water is 100 degrees Celsius at 1 atm at atmospheric pressure. Density: as water freezes, the molecules orientate themselves so that the volume expands and the density decreases. Ice forms a crystal lattice. Okay, so if we look at liquid compared to a solid, this is just water specifically. Liquid, you can see that the atoms are more densely, closely, tightly packed together. So that's what density implies, how closely packed, how tightly packed they are together. But in the solid, you can see there's less dense, right? The particles are further apart. Okay, decrease in density of ice helps to regulate the temperature of the earth and the climate. Ice floats on water, forming an insulating layer between water and the atmosphere, keeping the water from freezing. And it preserves aquatic life. Okay, so if you think of, I found this on the web. Okay, what you found on the web. If you think of like Antarctica, any place where there's ice on a top layer of water, that's the reason. Ice floats on water, forming an insulating layer between water and the atmosphere, keeping the water from freezing and preserving aquatic life. Otherwise, if all the water would freeze below the surface, there's no place for the fish to swim. Okay, crystal lattice sounds like a drug, in my opinion. Okay, so those are the properties of water and the amazing molecule of water. Okay, some examples. The table below identifies the dominant intermolecular force present in each case, so CO2. So we talk about intermolecular force. Remember that for each of these, right, it's not just one CO2 that would form an intermolecular force. It's when the CO2 bonds to another CO2 and multiple CO2s bond. That's when we have the formation of London dispersion, and then for that. So you can go through this table. Just some common examples of the intermolecular forces of each of these. Okay. Intermolecular forces and physical properties, right? So these are also very important. Let us discuss the phase of molecules. Intermolecular forces between molecules causes them to be attracted to one another. Strong intermolecular force equals strong attraction. Okay, so so yes, the stronger the intermolecular force, it makes sense, right? An intermolecular force is a force that is keeping the compounds together. Okay, so the stronger the intermolecular force, the stronger the attraction, because the stronger the bond is that's keeping them closely knitted, so the stronger they are attracted towards one another. Okay, at the same temperature, okay, The solid has a strong intermolecular force, liquid has an intermediate intermolecular force, and gas has a weak intermolecular force. So let's have a look at a temperature versus intermolecular force graph, okay, where it shows the intermolecular force increasing. So this is not exactly the water diagram that you guys learned last year. This just shows as the temperature increase, we have a decrease in intermolecular force. Okay, so we have a solid. Remember what's happening here? Why are we not seeing a change in temperature? Okay, during the melting and during the boiling point, this is where the phase is changing, right? All the energy is being used up to overcome the energy. All the energy is used to overcome the intermolecular forces. So that's why we're not seeing a change in temperature. Okay, I don't know if you guys remember this from the water graph that you guys learned last year. So that's why during the melting and boiling phases, the temperature is not changing, it's constant. The energy is being used to overcome the intermolecular forces. Okay, but it just shows, right, the intermolecular forces, how it changes according to the phase change of a particular compound. Oops. Hope no one on YouTube had any questions. Okay, how it's affected by the particular phase change, and it's to do it like density as well, right? Because as you can see with solid, they're more tightly packed together, liquid less, and gas much less tightly packed together. So therefore, when we consider intermolecular forces of gas is weaker than liquids, which is weaker than solids. Okay, we can consider this. Phase change, melting points. Melting points increase with intermolecular force, right? So the stronger the intermolecular force, the stronger the melting point. Boiling points also increase with increase in intermolecular force. So this is a relationship that's being formed, and this is the crucial takeaway from this. Higher the melting point and boiling point results in a higher intermolecular force. So there is a direct proportional relationship between intermolecular force and melting point and boiling point. Again, that's the important key takeaway from here. Let's have a look at this. Comparing hydrogen bonded to fluorine and hydrogen bonded to chlorine and hydrogen bonded to Br and hydrogen bonded to I. Okay, so this is a controlled experiment because we're only changing one thing. Right. Remember, we don't want it to be an unfair experiment where we're changing multiple things. So this experiment, this comparison makes sense because you're comparing how does hydrogen bond with fluorine, how does hydrogen bond with chlorine, how does hydrogen bond with bromine and iodine. Okay, so let's look at the written. Hydrogen HF. Okay, so firstly, if we look at the diagram, temperature on the left, we can see that I'm not sure, excuse me, if this is the melting point or boiling point, but we can see that the temperature, okay, for HF, this is, let's just say the melting point, is the highest, okay? Then it's HI, then it's HBr, and then it's HCl. So let's read what it says. HF contains hydrogen bonding, therefore it has the strongest intermolecular force, therefore it has the highest boiling point. So this is to do with boiling point, okay? So due to HF, so if you remember FON bonding to H, we said that forms hydrogen bonding, and hydrogen bonding is actually the strongest type of intermolecular force. So that clearly has the highest boiling point, okay? HCl, HBr, and HI all contain dipole-dipole forces, and therefore the boiling point increases with molecular mass, okay? So the size of the molecule, essentially. So they all contain, so HCl, HBr, and HI contain dipole-dipole forces. So how do we know which of the dipole-dipole forces is stronger? We consider the molecular mass or the size of the molecule, right? It's actually indicated here. If you look at the size of the molecule, it says larger molecule equal larger electron cloud, which means stronger intermolecular force. So here is another relationship. These are key takeaways that we need to take away from this, is these relationships that are forming. So the the larger the molecule, the stronger the intermolecular force. The smaller the molecule, the weaker the intermolecular force. So here, iodine is bigger than bromine, which is bigger than chlorine. Iodine, bigger than bromine, bigger than chlorine. So that's why, even though these are all dipole, 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 dipole forces, the one for iodine, the intermolecular forces between HI are stronger, not between HI and HI and HI are stronger than bromine because it's bigger than bromine. And bromine is stronger than chlorine because bromine is bigger than chlorine. And obviously this is controlled. H is the same for all. But even though chlorine is the smallest, it contains a type of bonding called hydrogen bonding, and therefore it makes it the strongest bond. Okay, so I guess we can highlight this. Melting points increase with EMF, boiling points increase with EMF. Okay, that's the relationship that forms. Evaporation decreases with EMF, decreases. Evaporation decreases with increase in EMF. Okay, high vapor pressures correspond to weaker intermolecular forces. This is another relationship. Okay, the higher the higher the evaporation, okay, the lower the intermolecular force. So this one is an inverse relationship. Okay, I'll answer your question in a bit. Let's talk about adhesion. Adhesion defines as it is the intermolecular attraction of molecules to molecules of a different substance. Example, water to glass, that's a liquid, to a solid. The strength of adhesive forces are dependent on the two specific substances interacting with each other. Okay, let's talk about cohesion. Cohesion is the intermolecular attraction between molecules of the same substance. Example, between water and water. Stronger intermolecular forces, greater cohesive forces. They don't explicitly mention a relationship. Is there only hydrogen bonding between FON? Yes, that is correct. Only F, O, or N. When hydrogen bonds with F, O, or N, that's the only time it forms hydrogen bonding. Okay, it's fine. You won't need to know it. Okay. But yeah, what's highlighted is important relationship between cohesion and intermolecular forces. The stronger the intermolecular forces, have greater cohesive abilities or greater cohesive forces. Let's look at capillarity. Capillarity, whatever. Okay, geez. Capillarity is the tendency of a liquid to rise in a very thin tube. This action occurs when the adhesive forces are stronger than the cohesive forces. Okay, so strong intermolecular forces between the liquid and the tube results in a greater capillary action. Okay, so understanding these relationships are very important. Okay, these are the main takeaways. Okay. Size of molecules, we already went through this. The larger the molecule, the larger the electron cloud, which means stronger intermolecular forces. Is it bigger because of its place in the periodic table? That is definitely correct. Remember, I will put this in these notes as well. There are certain trends in the periodic table. Okay. Let's see quickly if I can find it. I'll just Okay, I'm resharing my screen. Okay, here we go. So yes, this is the atomic size trend on the periodic table. As we move down and left, we move in the increasing direction of atomic size, and obviously moving to the right is decreasing atomic size. Okay, so this is the trend of size of each element in the periodic table. So when we compare fluorine, chlorine, bromine, iodine, you can see that we're moving downwards, right? I believe fluorine is here, chlorine, bromine, iodine, right? So moving downwards in the periodic table results in bigger, larger molecules. Okay, so here's the trend here, and that's how it. So obviously this would have this compound would have the greatest intermolecular force compared to all of them. Okay, just because it's the largest molecule. Let's discuss density. Density is the number. So I hope that answers your question. Density is the number of particles per unit volume. Increase intermolecular force increases the attractive forces between the particles, causing the particles to become more tightly packed. The arrangement of the particles determine the number of particles per volume, thereby determining density. So the relationship here is stronger intermolecular force, particles closely together, greater density. So the higher the density, the stronger the intermolecular force, right? And we can see like gas, liquid, solid type thing, right? Going from low density to high density, that would increase the strength in intermolecular force, which makes sense because if they're more closely packed together, the closer, their bonds are going to be closer and they're going to be stronger. Let's look at viscosity. Viscosity is the liquid's resistance to flow, right? Like how thick a liquid is. Stronger intermolecular force will cause the molecules in the liquid to hold together more strongly, causing the viscosity to increase. So the stronger the intermolecular force, the greater the viscosity, and vice versa for all of these, meaning a higher viscosity would mean that that compound has a stronger intermolecular force, right? So all these highlights in pink are very important relationships between the certain properties and intermolecular forces, right? That's what we care about. Let's look at thermal expansion. Thermal expansion is the expanding of a material when heated. As the temperature increases, so it's the ability, how much can the material expand when it's heated, right? That's the thermal expansion. As the temperature increases, the kinetic energy of the molecules increase. This additional energy can overcome the intermolecular force and molecules move further apart. A stronger intermolecular force equals molecules held together strongly equals lower thermal expansion. So the lower its thermal expansion ability is, the stronger the intermolecular force. So the less likely it is to expand when heated, the stronger its intermolecular force, because that makes sense, right? It's resisting to expand because the forces between it are strong trying to keep it together. Okay, let's look at solubility, which is also important. Solubility is the ability of a solute to dissolve in a solvent. A solute will dissolve in a solvent with similar intermolecular forces. We call it like this, dissolves like. Polar and ionic solute will dissolve in polar solvent. A non-polar solute will dissolve in non-polar solvent. Okay, so these are the key important takeaways. A solute will dissolve in a solvent with similar intermolecular forces, like dissolves like. Hydrogen bonding dissolves in hydrogen bonding. Okay, then we have polar and ionic solute will dissolve in polar. So polar dissolves in polar. And a non-polar solute will dissolve in a non-polar solvent. Non-polar dissolves in non-polar. Let's look at the last one, surface tension. Surface tension is the cohesive forces between molecules on the surface of a liquid. Okay, molecules at the surface of a liquid experience only inward intermolecular forces, and the relationship is the greater the surface tension, that means that the greater the intermolecular force, or the greater the intermolecular force, the greater the surface tension, right? It says the cohesive forces. Remember we said cohesion is the intermolecular attraction between molecules of the same substances. So here, okay, surface tension is the cohesive forces between the molecules on the surface of the liquid, and it's bonding to the inside water molecules, okay, because it's cohesive forces between molecules of the same substance. Okay, molecules at the surface of the liquid experience only inwards intermolecular forces. So the greater the surface tension, right, the greater that they are attracted to one another, right, the greater the intermolecular force. Okay, so you need to know all of these relationships. They are very important, highlighted in pink. Basically, like what's the relationship between the cohesion, okay, and the intermolecular force? What's the relationship between viscosity and the intermolecular forces? And once you know these relationships, direct or indirect, they will test it to you in experiments, okay? They'll test it to you in experiments and you have to compare them, right? And you will have to say, for example, compound X has a higher viscosity, therefore a stronger intermolecular force, or any other of these examples, okay? If you don't understand anything, please ask your question. But yes, intermolecular forces and physical properties then. Yeah, okay. So that concludes this section. I'm just thinking, I don't know if you guys want to do a question or you guys want to move on to the next topic. Just let me know in chat, I guess. But for now, let's have a look at this. I don't know if many of you have attempted to draw these, okay, but I did promise to not be lazy and create just a few steps that would allow you guys to question, as in an exam question, so that you guys understand how they answer, how they ask. Even I can try and spend half the next lesson doing that. Okay, I'll do that in the next lesson. Okay, so let's have a look at the steps. Okay, we're going to read through them first, and then we can do it with some examples. Right? I'm not going to do, yes, can we please do one now because we're writing chemistry tomorrow. All right, no sweat, we shall do one. Okay, so okay, so we're going to go through the rules, very important, and then we're going to go through the rules with regards to some of the examples. Okay, we're not going to do all. You guys can go practice some. But you'll get the concept, right? So let's read through the rules. This is a structured approach to drawing Lewis dot diagrams. The first rule is to count the total valence electrons, okay? And keep in mind, okay, so that's easy, right? Because remember we said the valence electrons we get from where? We get from the periodic table, okay? We get it from the period number in the periodic table, Roman numerals, okay? That tells us the valence electrons. However, just keep in mind that for positive ions, we have to subtract one electron from the total. Oh, sometimes not one, depending on the charge. If it's positive 1, you subtract 1. If it's positive 2, you subtract 2 electrons. So for each positive, so for each extra charge, you would subtract 1 electron. And for negative ions, you would add 1 electron because it gained an extra electron, okay? Number 2, put the least electronegative atom as the central atom, right? Remember we said that doesn't always work. So when does it not work? So put the least electronegative atom as the central atom. That is with the exception of with hydrogen, okay? Because hydrogen always goes on the outside, okay? So we do not put hydrogen in the center. In certain cases, we will find that hydrogen will be the least electronegative atom, but hydrogen always goes on the outside, so it doesn't matter, okay? Number 3, place 2 electrons between all atoms to form a chemical bond. Okay, so that we're forming our first chemical bond. Number 4, which is known as the octet rule. Okay, we discussed it. We didn't label it as the octet rule, but we discussed what the octet rule basically is. All compounds want to complete their orbitals to 8 electrons. All compounds want to complete their orbitals to 8 electrons. Okay, so yeah, they want to complete their orbitals to 8 electrons. So fill each outside atom with 8 electrons. So this is a slightly different approach, and I'll show you how it works. Fill each outside atom to 8 electrons. So add them up. They must all add up. Because remember, we already have, in step 3, we place 2 electrons to form the chemical bond between the atoms. But now we're going to fill them up to 8 electrons. Okay. However, there are certain exceptions to that as well. For example, it says there are certain exceptions. Example, hydrogen only needs 2 electrons to complete its orbital. Okay, we know that. Okay, and there are other exceptions, and unfortunately, we don't know. You guys don't learn enough chemistry to know the exceptions and know why the exceptions and to easily identify the exceptions. The way you need to learn it, unfortunately, the chemistry syllabus, I've always said this, is a very incomplete syllabus in high school. It's annoyingly incomplete, which results in a lot of confusion, right? Sometimes things just don't make sense. And then you learn 7 billion questions, and then in an exam, they still find a different way to ask it. Okay. It's just unfortunately the syllabus, there's a lot in chemistry, and like, yeah, some things are really just incomplete. Okay. So for example, these exceptions like BH3, PCl5, right? Just you're going to do some examples and you're going to come across some examples. Always just take note of the exceptions. Okay. Number 5, if the central atom does not have an octet, move electrons from the outer atoms to form double or triple bonds with the central atom, right? We did some examples with that as well. So let's follow that same rule with hydrogen. Okay. So number 1 is to count the total number of valence electrons. So it's basically 2 times 1, which is 2. Right. Put the least electronegative atom as a central atom. Of course, this is a non-polar molecule, so none of them are more electronegative than the other because it's both hydrogen. This contributes 1, this contributes 1. Okay, in this case, obviously, this is a really simple example with no need for all of the fancy stuff. Okay, it ends there. We don't need to do this. We just do that. There's no need for that because it's an exception. There's no need for that. Okay, so that's a really simple example of hydrogen. Okay, now let's do fluorine. Okay, so total valence electrons, I believe that there would be 14. Okay, total valence electrons 14. Put the least electron, okay, so that's fine. If this is going to be a non-polar molecule, hydrogen always goes outside. Put 2 electrons to form the bonds. So I'm going to form the bond, one from one fluorine, one from the other fluorine, and place 2 electrons to form the bonds. Done. Fill each outside electron to 8. Okay, and then we can count to double check how many we have. 1, 2, 3, 4, 5, 6, 7. So 7 times 2 is actually 14. So therefore, we indeed have the correct answer. We have a total of 14 electrons. Okay, let's do this now. These are non-polar molecules. Let's do it to the polar molecule. Okay, let's compare hydrogen and oxygen. Okay, so count the total valence electrons. The total valence electrons would be 2 into 1 plus valence electrons on oxygen, I believe, is 6. So it's going to be 8. 8 in total. 8 valence electrons in total. Okay, the next step is to put the least electronegative atom as the central atom. So let's compare hydrogen and oxygen. So hydrogen and oxygen, you can see that hydrogen is actually the least electronegative atom, but it's not going to be the central atom. Why? Because of that exception, right? It's not going to always work because hydrogen always goes on the outside. Hydrogen always goes on the outside. Okay, now let's follow that same rule, right? What's the next step? Okay, so we did this with this exception of hydrogen. That's the one we followed. Place 2 electrons between all atoms to form a chemical bond. So here, 2 electrons, 2 electrons. Okay, then it says for each outside atom to 8 electrons, the outside ones. That's 8. That's 8. Okay. So we've used, did I do something wrong? We've used, oh yes, I most definitely did something wrong. Okay, so here we go. Okay, again, then there's like a weird thing with this. Even though step 4 says octet rule for each outside atom to 8 electrons, there are certain exceptions. Hydrogen only needs 2, right? So that's where this comes in, right? There are certain exceptions to the octet rule. Hydrogen only needs 2. Okay, so that's what I did wrong. I filled hydrogen with 8 when there's no reason to. Okay, so hydrogen already has 2 because it's bonded with this oxygen. Okay, since it's bonded with that oxygen, it's already happy, right? It only needs 2, right? So instead of filling the outside with the extra valence electrons, what we do is we fill the oxygen with the extra valence electrons, right? Remember, these are called lone pairs, and these are our bonding pairs. Okay, and that's done. Right, so again, like I said, structured approach with like 700 exceptions. So how structured you want to call it, but it's decently structured. Okay, I'll give it that. It's decently structured, and it can really help you if you're struggling to draw these. Okay, so let's not bash it all that much. Let's look at NH3. So count the total number of valence electrons. The total number of valence electrons is going to be, I believe that's 5 plus 3 into 1. So that's going to be 8. Okay, so least electron. Sorry, I'm not following the rules. Count the total valence electron. Put the least electronegative atom at the central atom, except hydrogen. Hydrogen always goes on the outside, so that's our exception. So H is going to be central atom, and then we have N is going to be central atom, and then we have H all around it. It's late. Okay, then number 3, place 2 electrons between all atoms to form a chemical bond. Okay, let's do that. Okay, and then fill each outside atom to 8 electrons. So this is hydrogen. It does not need to be filled, okay, because it follows this exception. Hydrogen only needs 2 electrons, so it doesn't follow the octet rule. It's an exception to the octet rule. Okay, so these are happy chappies. Okay, then we have 1, 2, 3. So 3 times 2 is 6. We've only used 6 electrons. Okay, and that's where the next 2 come in. We put them here. Okay, they become a lone pair on nitrogen. Okay, so if your outside atoms are hydrogen, then your extra electrons would go to the central atom as lone pairs. Okay, let's look at HF. Count the total number of valence electrons. So we have 1 plus 7, which is 8. And we have hydrogen bonding with fluorine. Then the next step is to form the bond between them, and to fill, then after you form the bond between them, the single bond, fill in. Okay, I don't know why I'm doing the similar examples. I should do the different examples, and you guys can practice the rest. You fill in the rest. So hydrogen is happy, so I'm going to fill up fluorine with the rest. Okay, so fluorine has 8, hydrogen has 2. We have a total number of 8 valence electrons used. Everyone is happy. Life moves on. Nobody is sad. Okay, let us do CO2. Let us do N2 and CO2. Okay, let's have a look at N2. Okay, let's follow the rules for N2. So let's count the total number of valence electrons. I do not know that. It has 5, so the total number of valence electrons is 10. It's 2 times 5, which is 10. Okay, so then we have nitrogen and nitrogen. Then the rule says, so you count up all the valence electrons and add a single bond between them. Right, add a single bond between the 2. Okay, and fill the outer electrons with the octet rule, right? Fill them with 8. So I'm going to have 1, 2, 3, 4, 5, 6. 3, 4, 5, 6. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. Clearly, I've gone overboard, so this does not make sense. Okay, in this case, I have to get rid of that and that, I believe. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so these are all my electrons. These are all 10 of my electrons. So that's why counting the electrons can prove helpful. Now, in this case, right, it says the next step is if the so we followed the octet rule, right? However, if we have to consider each nitrogen does not have 8 valence electrons. Each nitrogen has 6 valence electrons, which is a big problem. Okay, this is indeed a big problem because we need to have 8, right? It needs to follow the octet rule. It needs to fill up all eight electron spaces in its orbital. Okay, so that's when we go to step number 5. If the central atom does not have an octet move electrons from the outer atoms to form double or triple bonds with the central atom. So obviously this is a bit of a weird example because our central atom, there's no really central atom, but both are like our central atom. But all that's telling us to do is to form more bonds. Okay, wait. So let's form another bond. So let's take one here and one here. But as it is, you can see that there's already this weird lone pair, which doesn't look right. And then when we count it again, right, remember to consider that when there is valence electrons being shared, when there's this covalent bonding taking place, to consider the amount of electrons a particular atom has while it's bonded, you consider all the atoms, including the bonded ones from the other one. That's what you count. So here we have 1, 2, 3, 4, 5, 6, 7. Again, it's not 8. So that's when we have to try and form another bond. Okay, so I think this structured method, hopefully it's making sense, right? When you don't have 8 electrons on the central atom, you take electrons from the outer. So basically maybe the ones that I use as like lone pairs. Let's make this bigger. Make a circle bigger. Okay, you take from the outside and you create double or triple bonds. And this is exactly what we did, right? We had to create a triple bond because now when we count it, we have 1, 2. Okay, let's count it just for a single nitrogen. We have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8. And then for the other nitrogen, now we also have 8. Okay, so I hope that this method is making sense. Let's do 2 more, right? We're going to do one of these exceptions, BH3 and CO2. So let's do BH3. BH3, place the most electronegative. Okay, so count the amount of electrons first. So boron has 3. So 3 plus 1 into 3, which is basically 6. Okay. Place the least electronegative atom in the center, unless you're working with hydrogen. Hydrogen always goes on the outside. So B H3. Okay. Then it says form a bond between each atom. Okay. And then once you form the bond between each atom, so place 2 electrons to form a bond, a chemical bond. Octet rule, fill each outside atom to 8 electrons. There are certain exceptions. Hydrogen only needs 2. And compounds like BH3 so we're actually dealing with one of the exceptions. So firstly, I can't fill the outer electrons. I can't fill the outer atoms with 8 because they're hydrogen and they're happy with 2. So since hydrogen is happy with 2, I need to fill the remainder of the electrons on the central atom. But I noticed that I don't actually have any extra electrons left over. I've used all 6. And then you just start crying because this is actually an exception to the octet rule. This guy is perfectly happy the way it is. So what's the problem? The problem here is that boron does not have 8 valence electrons, but it's an exception. It's happy. And yeah. Okay, let's look at PCl5. P, phosphorus, has 5 valence electron. So we place the least electronegative atom in the center. That would be phosphorus if we're comparing phosphorus and chlorine. Phosphorus and chlorine. Phosphorus gets placed at the center. Okay, 1, 2, 3, 4. Okay, so place the least electronegative atom at the center. Done. Next step is to form a bond between each one. Okay, we forgot step 1, which is count the amount of electrons. I'm going to do that now. Okay, so I've formed a single bond between each one. Count them. We said P has 3, I think, or 5. No, we said it has 5. 5 plus, we have 5 chlorines, so 5 times 7, which is 35 plus 5, which is actually 40. Okay, so out of the, so it says form a single bond between, form a bond between each atom, and then complete the outer orbital. So 1, 2, 3, 4. 5, 6, and then 7, 8. And then 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. So we just have to complete it to 8, right? We're not adding another 8 to make it 10. 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Finally, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so here we have followed the rules up until number 4. Okay, where we filled each one with 8. Okay, so that's done. So let's count up now how many electrons have we used. So this should be 8. That should be 8. That should be 8. That should be 8. That should be 8. Okay, so 8 times 5 essentially is 40. So we've gotten to a point where we've used up all of our valence electrons. But now, if we have to consider our central atom, phosphorus, it has 2, 4, 6, 8, 10 valence electrons. How is that possible? We don't know. We don't care. Okay, we know why technically, but this is an exception as well. So this is able to store 10 valence electrons. It's called something called an extended octet. Okay, but it's not something you need to know. Okay, however, you do need to know that it's an exception. So these are exceptions. Okay, so know these exceptions, and if you come across any more, looking at the mammals, you can judge whether it's an exception or not. But one of them is 2 different types. Like one of them is an incomplete central atom, right, with less than 8, and one is with more than 8. Okay, let's do our last and final one. Carbon dioxide. So carbon dioxide, place the least electron. Okay, first count the electrons, and then place the least electronegative atom in the center. That would be carbon. If we're going to compare that and that, we can say that's 2.5, that's 3. So the least electronegative atom in the center. Okay. Count up the electrons first, whatever they're called, who cares? I think it's 5 plus 2 into 6. I might be totally incorrect. I am probably incorrect. It's 4. This is equal to 4 plus 2 times 6 is equal to 16. So we have 16 valence electrons. Let's place the least the least electronegative atom in the center. Okay. Then the next step, form a bond between each. Okay, this is incorrect. Let's do this. Okay, form a bond between each. Okay, and the next step is to fill up the outermost orbitals. To fill up the outermost orbitals with 8. In this case, we're dealing with oxygen, so we can do that. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so let's count up our electrons once more. Here we've used 8. Here we've used 8. So that's 16. We're done. We cannot use more electrons. Okay. Since we cannot use more electrons. Okay, so we're done with electrons. So now we consider to see if each thing has 8. So oxygen has 8. Each oxygen definitely has 8. But when we consider our central atom does not have 8. So that's when you have to go to step number 5. If the central atom does not have an octet, 8 electrons, move electrons from outer atoms to form double or triple bonds with the central atom. So here I can see that it's missing 1, 2, 3, 4. It's missing 4 electrons. So I'm going to form 2 double bonds. Okay, I'm going to I have an extra electron 2, 4, 6, 8, 10, 12, 14, 16. Ah, yes, this should not be. See, it's not even possible. Because, like, for example, this, the way I've drawn this is completely incorrect. Because here I'm assuming that 7 electrons come from oxygen, which is not the case, right? So automatically, like, that should tell you. But either way, in that case, if you're just using all circles, right, then this method would work. But that's when you would now take 2, you would move. Okay, let's do it in terms of only circles, so it makes more sense. Okay, so we followed the rulings up until now. We've created a single bond between each atom. Okay, but now the central atom doesn't have 2, so that's when we start taking bonds from the outside to form double bonds. These lone pairs, we use it to form double bonds. Okay, and that's the example with carbon dioxide. Can you do an example that involves brackets? Can you give me an example? Okay, in CaF4, where's the bracket? Okay, NH4, PH4, PH4 plus. Okay, so PH4 plus, that's an example. Is that an example of dative covalent bonding? Okay, NH4, PH4 plus, NH4 plus. Okay, so these are examples of dative covalent bonding. So, I don't know. I don't think I need to do it. You guys let me know if you want me, but I would feel that you follow this. If you follow the dative covalent bonding of this, it would make sense. Okay, where we have NH3, which we can draw, right? NH3 we can draw. Remember, N has 5. Okay, each hydrogen comes with 1. We fill in the outermost. Remember, when we fill in hydrogen already on the outside, then the extra electrons would go to the central atom as a lone pair. So we form NH3, right? We notice that NH3, what is dative? CO3 -2. Okay, we can do that. That's the carbonate ion. Okay, what is dative? This guy is a clown. Okay, with regards to past paper, I'm gonna go through it in a second. Sorry, I'm just tired. With regards to a past paper, look, I don't think I have time to do a past paper, unfortunately. I have work myself. I need to go do work. What I would just go and do a past paper yourself. All right. What we've learned should be enough for you to do decent in a past paper. If you have any questions, message me. I will respond to you. Okay, let's have a look. Let's just go through dative of covalent bonding one more time for this clown. Okay, a covalent bond is formed when one atom donates both a coordinate bond, a coordinate or dative bond is formed when one atom donates both electrons to form a bonding pair. The filled electron orbital lone pair of one atom overlaps with the empty orbital of another. Example, H3O plus, NH4 plus. Those are the main examples that you need to know. Just give me 1 second. Okay, so, and then with regards to CaF4, we can do CaF4, okay. Another thing is with regards to, like, for example, CO3 to the power of 2 minus. This is not something that will be examinable, okay, because specifically in your guide, okay, just give me 1 second, I'm going to fetch a highlighter. Okay, in what's required for you to learn, I'll read it for you word for word so that you have peace of mind. Okay, first thing is draw Lewis dot diagrams of elements. Easy peasy. Okay, elements, you just need to know the amount of valence electrons and draw them around. The thing you need to know is that per coordinate site, you draw one each, right? So you won't, okay, what I'm talking about is, you won't need to draw, for example, Cl, it has 7, you can't draw it like this. Or let's just say, I don't know, oxygen has 5. You can't draw it like this. This is wrong, right? You have to draw at least one per side. So this would be the correct one for oxygen. If it has 5, I'm pretty sure it has 5, right? So that's for elements, okay? Determine the number of valence electrons in an atom. Okay, I might as well ask you to do 2 plus 2. Explain in terms of electrostatic force and energy why 2 hydrogen atoms form an H2 molecule, and it does not, we don't have He2, so we need to know noble gases, right? Remember we discussed noble gases. Noble gases are non-reactive, okay? It's fine, interpret the graphing potential and distance nuclear, covalent molecule. Okay, then you are required to draw Lewis diagrams for simple molecules. These are not my words, okay? Example, H2, F2, H2O, NH3, CH4, HF, OF2, HOCl, and molecules with multiple bonds, N2O2, HCN. Okay, so the simple examples is what you are required to know. So you're not going to get something complicated that's going to make you consider things that are out of syllabus in order to solve. Okay, then of course discuss the shapes, whatever. Anything else? Okay, so simple molecules. You're not expected to go into intricacies where there are other factors that you need to consider in order to determine the shape. Okay, now that being said, okay, that being said, let us at least do all of the examples that have been mentioned here. Okay, and then let's end, okay, because I really need to go. Okay, so dative covalent, we went through the explanation. Now let's go through the diagram. Okay, so basically, Mr. Saad, dative covalent bonding is when we have a guy like you that comes with no knowledge. Okay, I mean, sorry, not no knowledge, no electrons. Okay, this poor guy is a hydrogen plus. It is a hydrogen ion. Okay, and remember, hydrogen as it is only has 1 electron. Okay, so the hydrogen plus, the plus indicates to us that it has lost an electron. That's why it became positively charged. So this poor guy doesn't even have an electron, right? So that's why it becomes H plus with no electrons. Okay, so H plus, he has no electrons. So when it takes part in covalent bonding, he has nothing to donate. Okay, so when this guy reacts with something like NH3. Now, if you look at, okay, sorry, this is H2O actually. If you look at H2O, water, okay, H2O has 2 lone pairs. Okay, so it has 2 pairs, 1, 2, that are sitting around doing nothing, not bonding with anything. So this is like the perfect match because we have one guy that has no electrons, and then this molecule that has just this lone pair just hanging around. Okay, what happens is this H plus molecule then goes and bonds with this H2O molecule. It does not donate any electrons, but because this H2O has a lone pair, it has the ability to bond with a hydrogen without the need of the hydrogen donating an electron. So this H2O can donate both electrons to form the bond between this third H. And that's exactly what happens here. So the hydrogen comes in with no electrons, but because it's bonding with something that has a lone pair, the lone pair of this molecule can form the bond between the hydrogen and that molecule. I hope that makes sense. If you don't understand, please let me know. I'll explain it again. Okay, so this guy comes in and bonds basically to this one here. Okay, what does it say about dative? Okay, describe the formation of a dative covalent bond. Yes, and the example in which you will be given is most likely going to be H3 or NH4 plus. If it happens to be another type of covalent bond, it will be obvious because you will have to have one part of the covalent bond forming coming in with no electrons, right? That's the whole point of dative covalent bonding. One of the atoms or compounds has no electrons to donate, no electrons to take part in bonding, and therefore the other compound will use two of its own electrons to form the entire bond. Okay, so the same thing can be seen with ammonia forming the ammonium ion. So you said draw NH4 covalent bond. This is how you would do it, right? You're adding an H plus ion, which has no electrons, to an NH3 atom, an NH3 compound, sorry, which has this lone pair just chilling. So the hydrogen comes in, okay, no K in the world, and bonds with that. Okay, now let's look at CAF4. So CAF4 should, okay, so I hope you understand dative covalent bonding. Then just to answer like one or two other questions. Okay, we can do it here. Okay, this doesn't have brackets, by the way. You mentioned something about brackets. But where does the plus come from? Which plus? This plus here or this plus here? Outside the bracket, so this plus here. Okay, so because you're adding in your hydrogen ion into this compound, it would become positively charged. All right, there's probably a deeper explanation as to why, but it's not important. It shouldn't be so important. Just note that in all your dative covalent bondings, it's going to become a positive ion. Okay, you adding a positive hydrogen ion into this compound, okay, which comes with no extra electrons. Okay, so this guy is donating basically both electrons. Okay, that's not a fourth hydrogen, but it's donating both electrons. But it's fine. In this case, there's still two extra electrons. That's fine. Okay, that's okay. The main thing is this, the guy coming in with no extra electrons. That's the main thing. Whether it has an extra lone pair or no extra lone pair, that doesn't matter. Okay, that's the main part of dative covalent bonding. Okay, let's look at CAF4. CA, okay, let's look at CA. CA is going to have 2 in F4. Each F has. Did you make up this compound or is this actually a compound? F has 7. This is not a compound. This is not possible. Sorry, Ca. I think, were you talking about CF4? Because CF4 is then possible. Okay. Let's look at CO3 to the -2. Okay. So this is an ion. Okay. So let's follow our steps and let's see if this is within syllabus, right? Let's see if we have enough information to solve this question. Just give me 1 second. Okay. So C, the person who said CaF4, not a compound. Okay. If we have to consider CF4, then that's possible, right? I'm not going to draw it, but you have 4 of these. Okay. Clearly, each one can bond with a fluorine, just like that, right? And then you just multiply that by 4 on each side, and you'd get the compound for CF4. Okay. Let's have a look at this. Let's follow it step by step. Count the total number of electrons. So here we have carbon, which has 4. So it's going to be 4 plus oxygen. Each oxygen, I believe, has 6, I think. Six. Okay. And then 2 minus means it has 2 extra electrons. So I will have to add 2. Okay. So here we have 4. 6 times is 18 plus 2. So 24. Okay. So we have 24 electrons. Okay. Least electronegative atom in the center, that's going to be carbon. Carbon in the center. Okay. Carbon in the center. Bonded with 3 oxygens. Oxygen. 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 Okay. Bonded with 3 oxygens. Okay. And now we need to create a bond between each one. Okay. And fill the outermost orbitals with all its electrons. Okay. Okay. So I'm just following step by step. If I missed out any step, please let me know. Okay. It's technically incorrect, I know. So let's just use all circles. Okay. And the fact that that's incorrect is indicative. It indicates to us that something's wrong and we need to form a bond, a double bond or triple bond somewhere. Okay, so I followed up until here. You should be able to get very easily. I'm following rules. Okay, I'm following the 5 steps that I gave you. Okay, so now that I've done the octet rule, and again, technically it's incorrect because carbon has 4. Okay, so carbon just has a weird one chilling around there. But okay, we're not doing that, right? We're not focused on that for now, right? We don't care about that for now. We don't care how much comes from carbon. We're just using all circles. Okay, don't use X and O's when it comes to these complicated examples because you're going to confuse yourself. Just use all circles, right? Even though this doesn't make sense because carbon should have an extra, and then oxygen only has 6, right? So where all of a sudden did he get 8 from? But we're just following the rules. Okay, we counted the total valence electrons. For positive ions, we subtracted 1. Remember, if this one was okay, and for negative ions, you add 1. This one was -2, so we added 2. Right. Then number 2, put the least electronegative atom as the central atom. Put the least electron. So that's what we did, except with hydrogen. Hydrogen is on the outside. We didn't have hydrogen, so that's fine. Number 3, place 2 electrons between all atoms to form a chemical bond. We did that. And then we followed the octet rule to fill each outside atom to 8 electrons. We didn't have to worry about hydrogen. We didn't have to worry about the exception. Then number 5, if the central atom does not have an octet, move electrons from outer. Okay, so now we have to follow number 5. We have to check, does our central atom have 8 electrons? And of course, we expected it not to, just because these oxygens got electrons that they didn't even have. Okay, so we have to shift it around in a way. We have to move these bonds around in a way that the central atom has the central atom has 8 electrons. Okay, so currently it has 6, so it only needs 2 more. So what I can do, okay, is I take one of the bonds from one of the oxygens to form a double bond with carbon. Okay, and now carbon has 8, this oxygen has 8, this oxygen has 8, and this oxygen has 8. Everybody's happy. Okay, so it's a strange example where only one of the oxygens that form with carbon contain a double bond, but nevertheless, it's an example. Let's double check our electrons. We need 24. Here we have 8, here we have 8, here we have 8. 3 times 8 is indeed 24. Okay, I personally do not think that they will ask this. I personally do not think that they will ask this, but there, following the rules, there's your example of CO3 2 minus. Okay, just really quickly. Okay, I have all the examples that I need from this thing. So I don't want to do more because I feel like I've done enough for you guys to follow the rules and be able to do it. If you stuck, please message me and then I will explain it to you. But I feel like I've done enough of these examples for you guys to have enough practice on your own. And the answers are here. It's not like the answers are not here. Okay. Just NO3 minus, I'm going to fix. All right. I wanted to do one example with a negative. Okay, I'll fix the memo. You guys can try it out, follow all the rules, and you'll get to the answer. Okay, with the other two given as well, that example. Okay, cool. Any other questions before we leave? Sorry, I don't have time to do a question. Exam question, we're already half an hour over, and I'm eating into my time. So yeah, go practice a question. If you have any questions, message me. Don't be lazy, Saad. Okay, any other questions though? I think this was a good example. This is like as hard as it probably can get. And if you understand this, then you should understand the rest. Hello, anyone? No? Everything's fine? Do you guys understand this example? Okay, cool. Okay, perfect. Okay, cool. Thank you guys so much. Then let's end it there. Okay, it is very late. Good luck. Please go and practice examples. Go and do a past paper. If you're writing tomorrow, go do a past paper on all the topics. Do a past paper on all the topics, and yeah, all the best. Thank you guys so much for staying for an extra freaking 35 minutes. Okay, sorry for keeping you guys so long, but I hope that you understood. Cool. Thank you guys so much for joining. I will see you guys next week.